All right, shall we get started? So, did you check the project number 1 on Canvas? Good. There is something unclear. That's what basically the recitations and office hours are about. So, I encourage you to talk to the TAs. Like, if you're embarrassed to ask something that I already explained 3 times, that's a good opportunity to ask. But you don't really have to be embarrassed. It would be weird if you didn't get confused in the coordinate system, because I think it's normal to get slightly confused as long as you can get the good matrices and the correct transformations back eventually. So the next project and the next topic is going to be solving systems of linear equations. It's the fundamental problem in linear algebra, and it's used in many applications. For example, when you will be studying physics-based animation, when solving fluid flow and many other things. What you will eventually end up with is a system of linear equations that needs to be solved. It needs to be solved efficiently and robustly. And it all starts with this basic theory. So actually there's when it comes to linear equations, this is still fairly active. I don't know if research, but definitely on the technology side of things. There's the very efficient numerical libraries for solving systems of linear equations are still being developed, especially for the sparse case. We will get there why it's important sometimes to consider sparse systems. The good thing is that as long as you have MATLAB, you almost don't have to worry about it, because MATLAB already implements these efficient linear solvers for you. But if you will be doing something specialized, maybe doing fluid simulations or elastic body simulations or any computations in computer vision or robotics, chances are you will have to deal with systems of linear equations. So sometimes it's good to exploit the special properties of your particular problem. So that's also why it's good to understand what's going on. It's also related to what I sort of broached the last time, is the inverse matrix, right? So solving the system of linear equations can also be essentially viewed as finding an inverse matrix to the system. So that was just for introduction, and I will start with just to show you that there are some catches in solving systems of linear equations, which I can illustrate already in the 1D case. So that's the simplest, stupidest example of a linear system, where my system is actually not a system, where it's just a single equation. But you can already see there what are the caveats, what are the things we need to be aware of when we are facing such a problem. So instead of inversion, we can call it unmultiplication, because that's what it means, right? We are inverting the multiplication. So let's consider it doesn't get simpler. It wouldn't get simpler than that, right? So let's consider this equation. So there's just one unknown. We need to solve it, right? Obviously, I won't even ask, because it's obvious. There is just exactly one solution, right? And that you can easily obtain by dividing 10 by 5. So equation 5x equals 10 has exactly one right solution, right? That's trivial. Now what if I look at this equation, 0x equals 0? It still has a solution, but now it has infinitely many solutions, right? Any x, if I multiply it with 0, I get 0 back. So 2 is still going to be solution, 3, 4, whatever, any real number, including 0, is a solution. So that's actually a whole space of solutions, right? So with already one equation, there is something funny going on. And even other case, so that's a third case already, is that if I don't have 0x equals 0, but if I wanted 0x equals some number, for example, 5, then there is no solution all of a sudden, right? Because no matter what I multiply 0 with, I get 0 back. There's no way I could create there 5. So this equation has no solution, empty set of solutions. So already on this simple example, we see that there are at least 3 cases we have to consider, right? Because the matrix case, or the case of systems of linear equations, This will contain this, right? This is the simplest example. This is like 1 by 1 matrix if you want. You can always look at a scalar as a 1 by 1 matrix. So this will be there, and it will be there in a little more complicated form. So let's look at all the cases we had here for just the scalar case. So there can either be a unique solution, or infinitely many solutions, or no solution, right? And that's it. In this case, there can be no other cases. And it's good to have this picture in mind, because the same three cases will appear in matrix equations or equivalent linear systems. It just won't be as obvious, right? Here everybody really sees what's going on. In the matrix, to see that, it's usually not obvious. That's essentially what linear algebra is about, is to exposing this, making it obvious. All right, so let's look at some slightly more interesting example. And you probably have solved problems like this, right? So here is an example of a system. I have 3 equations and I have 3 unknowns, right? You remember it's good to have the same number of equations as unknowns. So we will first consider this case only. Later I will talk about the case when you have like more equations than unknowns, or the other way around, where the number is not equal. That will be slightly different. But for now, let's just consider this the case of square matrices, where the number of unknowns is the same as the number of constraints. So you probably know how to solve things like this, right? So the standard way to solve this is to apply Gaussian elimination. Is there anybody who never heard of Gaussian elimination? Okay, good. So we need to look at how Gaussian elimination works, because then we'll write it in matrix form, and that will give us some interesting results. So how to solve this? Let's look at the system. So the general idea of Gaussian elimination is to take the first equation, scale it appropriately, such that when added to the second equation, eliminates the first component, right? And then the same thing for the third equation. So for the second one, I need to scale it by -2, right? So I scaled the first equation by -2, and I sum it with this one. So let's verify that it really works. So the x has to disappear. That's the whole point. That's why it's called elimination. And here I get -8 plus 9 is 1. And here is 4 minus 3 is also 1. 1's that. The same thing I have to do for the right-hand side, right? So this will be -4 plus 8 is 4. Yeah, so that's how I got the second equation, this one. And for the third one, all I have to do is multiply this by 1, right? So this time multiplying just by 1, or doing nothing, if you will, and adding the equation, right? Obviously, if the thing have to be equal, they have to be equal even if I add them together and if I multiply them by a scalar, right? That's the idea behind Gaussian elimination. So what all I have to do here is take the first equation, scale it with nothing or with 1, and add it to the last one, and I get 0 here. That has to be that 1. And 5, yeah, that's correct. And this is 10 plus 2 is 12. Yeah, that's correct. It's always good to check it. Sometimes there might be mistakes, you never know. So this is the first step. So now we got this form. And this is an equivalent system of equations, right? So this is the first step, and we can do one more step. So here I just copied the system from before, so this is the form where we got it so far, and I can continue. So I'm already happy with the first one. Now I'm looking just at this part here, and I repeat the same idea, right? I scale the first equation appropriately, so by -1, and I add it to the last one. So what I get is -z plus 5 is 4, and here is 12 minus 4 is 8. So I get this equation back. And when I'm at this form, I am almost done, because let's see what happened. So I took this original system, and I algebraically manipulated it to get it to this form by adding and multiplying equations around, which is equivalent. The solutions of both systems have to be the same. And this one I can solve very easily by back substitution, right? It's sort of obvious. You start from the last equation, 4z equals 8. From that, you can obviously see that z is 2, right? So now I know that z is 2, so I substitute it here. Here I substitute 2, so 1y plus 1z means 1y plus 2, so equals 4, so it means that y equals 2, this. So now I know z and y, so I've substituted to the last equation. So here y is here 2, z is also 2, so what I get is 8 minus 2 is 6, is that right? And minus 4 is 4, 2 minus 4 is minus 2, so I get 2x equals minus 2, so I get x equals minus 1, yes, so that's correct. And this is my solution. So you can see here I was lucky. Here it was the case where I had exactly one solution, right? And that is the solution. It's trivial to verify it. You just plug it in there in the original system and verify that whatever you get on the left equals what was specified on the right, right? So simple stuff. So one thing that's good to notice here is that the back substitution, once we got it into the triangular form, it's very easy to solve, right? Just exactly because it's triangular, because we work our way upwards with the back substitution. So the last equation is really simple to solve, and once we have solved it, we substitute it up one level higher and work our way to get all the values eventually. I think this is really obvious, right? This is really like solving linear systems 101. You could be giving it like all sorts of like geometrical perspectives. I think this is elaborated on in the book. If you are interested, you can take a look. I think it's so simple that I personally wouldn't bother, but maybe there are some insights to be gained there. What I would like to look at now is the matrix perspective. Like this approach, like doing it by hand and writing x, y, z for the unknowns, it wouldn't really scale that well. You would very quickly run out of letters, if not anything else. So let's write it in matrix form. Here you'll actually be able to see that the matrices are like really convenient formalism for dealing with things like this. So in matrix form, this system can be written like this. So here, all that happened here is that I took the coefficients and I stacked them into matrix, right? 2, 4, minus 2, 4, 9, minus 3, minus 2, minus 3, and 7. So this is a matrix vector multiplication, which gives me exactly these left-hand sides, and the right-hand sides I stacked into a vector. Just hoping you wouldn't have to take notes as I'm recording it. If you like to take notes, please go ahead. The thing is, I don't know if you're like copying all this, that would take forever. So what is interesting now, we can look at the operations we were doing to the system. I was like algebraically manipulating the system to get it to the form where it's easily solvable, right? So we can look, what does it mean when working on this matrix? So let's do that. So here is how the matrix that corresponds to scaling one row and adding it to another row looks like. So this is still talking about that one example, and this is the matrix that essentially does it. So this matrix takes the first equation, scales it by -2, and adds it to the second one. So let's see how it works. So here I have a matrix multiplication. Here is my original matrix. That's my system matrix. And here is the matrix that performs the operation, the one step of Gaussian elimination. Does it have a name, this thing? Maybe like one elimination? I don't know. So let's look what this matrix does. So the first row, is multiplied with all the columns, right? So it means that the first row is unchanged, right? because the matrix 1, 0, 0 here, it means it does nothing to the first row. It just lets the first row through, right? Something interesting happens to the second row. So what happens to the second row is that I take the first row, multiply it by -2, and sum it with the second row, multiplied by 1, right? So the point of this is exactly so I get 0 here, right? That's my elimination, now written in matrix language. And the third row of this matrix, well, again, that does nothing. It just lets it through, right? It's just 0, 0, 1. So it just multiplies, so again, row times column, row times column, row times column. So there are zeros here, doesn't matter. And this just goes through because there is 1. So this matrix, if you look at it carefully, is basically a diagonal matrix with only one off-diagonal element. That's the -2 here, right? And these ones on the diagonal, they just say, take the original row, and this -2 would be saying, take some other row, in this case the first row, multiply it by -2 and add it to the row that was originally there. So that means that's sort of interesting if you think about it, because it means that the operation on the equations, which I was previously doing on paper, just by like adding these equations, it can be encoded as matrix multiplication with some special matrix. Which is nice, right? Because now you know you can do it as matrix multiplication. You can make your MATLAB happy. You just like code the matrix, and MATLAB can do it super efficiently for you. Now don't forget that the same thing, the same matrix, we need to apply to the right-hand side, right? Otherwise it would not be true. So if I manipulate this is the system matrix, this is my right-hand side, I need to obviously multiply both sides of the equation, right? It's just like with one single equation, I can do these operations and like add something to the left-hand side, add something to the right-hand side. I have to always do the same thing to both hand sides. So here is the result. So here is what I get by multiplying these two matrices. That's what I was trying to explain. So the first row and the third row are the same. And the second row got eliminated the first term here. So and the corresponding operation happened here. So here I took, what did I do here? The first and second are unchanged, and here I just did -2 times 2 plus 8, so it's -4 plus 8 is 4. So that was the first step. The second step takes the matrix we got before, so this matrix, now I take, and I put it here. This animation works. So this is the matrix I previously ended with, and I do another of these elimination operations. I still think there is some better name for it, but I'm blanking on it. It's just the steps of the Gaussian elimination. So what this matrix, so now we are trying to eliminate this -2 here, right? So this matrix lets the first row through, the second row goes also through, and the third row, that's the only one where something interesting happens. I take the first one and add it to the third one. So that's what this last part of the matrix does. So by adding these rows, obviously here I get 0. That's what I care about, and here is whatever is here, like 4 minus 3 is 1, and -2 plus 7 is 5. Again, the same thing I have to apply to the right-hand side. So it means that the 2 and 4, they are just copied. And for the last term, I have to sum 2 and 10, so I get here 12. So here I'm doing the same thing I did previously, except that now I'm doing it in matrix language. You will see why I'm doing that in a second. It goes to LU decomposition. We will get there. So now I take this matrix and I do the final step. Let's take a look what the final step will be. The final step has to eliminate this one here, right? So the first 2 rows I just copy, and the third row I add the second one to it. So I take the second row and add it to the third one. So that's what this last row does, right? So by now you have probably figured out that what the number here that is here, that's non-zero, means what do I have to multiply the row with, and where it is means which row I'm taking, right? If it's in the second column, I'm taking second row. If it's in the first column, I'm taking the first row. And again, the same thing I must apply to the right-hand side. So if I do this, if I add it, I get minus 1 plus 5 is 4. And the same thing here, minus 4 plus 12 is 8. And now I am happy because I got this, what is called a triangular form. This would be an upper triangular matrix. So let's look at this whole process together. So what happened here, what I was just explaining all this time, was that as a sequence of matrix multiplication, I started with this matrix here. First multiplied with this matrix, then multiplied with this matrix, and finally multiplied with this last matrix, and I got this matrix back. So that's really the magic of matrix multiplication. Not really magic, but that's really the point of matrix multiplication, the associativity. That if I multiply it all together, it's like multiplying by one big matrix. And I reduced it to what is called upper triangular matrix, because it looks like matrix. If you look like from far enough, upper triangular matrix looks like this. Here is something, some numbers, and here is zeros. All zeros everywhere in this part. It's upper triangular or upper triangle. And you can guess that there is also like a lower triangular matrix. We will need that in a second. And that means that here is some stuff and here is zeros. Lower triangle. So there can be always non-zeros on the diagonal. On the diagonal there's always something going on. And of the diagonal on one side there is all zeros, which is usually like one big zero. That's a notational thing. So this is a Gaussian elimination written in terms of matrices. It's also good to notice that these matrices corresponding to the individual steps, they always have this form. So it's always a diagonal matrix with ones on the diagonal, and only one of diagonal element corresponding to which a multiple of which row and what multiple of that row I am adding to perform the elimination. So the thing I was telling you at the very beginning, that there are actually these three cases, that either the system has a unique solution, no solution, or infinite number of solutions. That also appears in matrices, except that the infinite number of solutions can vary. So, for example, if you consider this system, it has an infinite number of solutions. If you think about it, this third row is just all zeros. So it's essentially, it wouldn't have to be there, right? It's saying nothing. It's saying that if I multiply x, y, and z all by zeros, then it has to be zero, but it always has to be like that, right? So it wouldn't really have to be there. So this is really only two constraints, two equalities for three unknowns. So obviously there is some leeway, right? If you are like curious, you can, is this right? Yeah. You can try to find like several solutions for it. The other way, it can also be like by like that. Sorry. It can also be the case that we have no solutions at all. That would be the case of this system, right? If you look at it, why is that? It's sort of obvious here, right? What happened here? Look at the second row. The second row wants y to be 4, right? And the third one, oh sorry, z to be 4, right? This is matrix vector multiplication. So this row says z be 4. The third row says that 4z is 8 or that z should be 2. There is no way I could satisfy both of these equalities, right? There's going to be either 4 or 2. So I cannot find a solution to the system. So it would be good to know which case are we dealing with, right? Can we compute the unique? If I give you a matrix, the first question you should ask, a matrix and the right-hand side. Actually, the right-hand side is important here. The right-hand side actually is what makes all the difference between infinite number of solutions and those solutions. The first question you should ask if there is a unique solution or the other case, infinite or 0. This like special case. And here is one thing we can immediately find out from the Gaussian elimination. So the Gaussian elimination is a really good tool because it converts the matrix to the upper triangular form, and we can immediately conclude that if there are non-zero elements on the diagonal, so the pivot elements, the things just above the zeros, then the back substitution will work, right? And because the back substitution will work, it means we will have a unique solution no matter what the right-hand side is, right? So if the Gaussian elimination succeeds in the sense that it gives me an upper triangular matrix, so those are the diagonal elements. Here are zeros here, and here is something going on here. I don't know what these numbers, they can be also zeros, but they can be also non-zeros. So if these guys on the diagonal, those are the pivot elements, if these elements on the diagonal are all non-zero, then the back substitution is going to work, right? So I can compute for any right-hand side, or any right-hand side B, I can back substitute and get my x back, right? So in this case, I totally, certainly have a unique solution. And if this is the case, now we are still talking just about square matrices. In rectangular matrices, it's a little bit more funny, and we'll talk about that later. So matrices which have this property that Gaussian elimination gives me non-zero, all diagonal terms are non-zero, then these matrices are called invertible or non-singular. And that also means that I can compute the inverse, right? I told you last time that not all matrices have an inverse, but these invertible means the inverse exists. And I will show you in a little bit how the inverse looks like in this case. Now, what is the other case? The other case is that there are some zeros along the diagonal, right? And in that case, we are in this like weird mode, which can be either zero solutions or infinitely many solutions. And that depends now on the right-hand side, which case it will be, if it will be 0 or infinitely many. But it's in either way, it's not going to be just like one precise solution. And matrices of this property are the non-invertible ones. That's where the inverse does not exist, or sometimes we call them singular or rank deficient. Let's take a look how the inverse looks like. So this is the matrix we got from Gaussian elimination as the upper triangular, right? And I told you that there is also lower triangular. That's like the symmetric concept to upper triangular. That means that all the entries above the diagonal are zeros. The ones below there, here could also be like 0. That doesn't matter, right? But that here can be something. Here must be zeros. That's the point here. And here is an interesting thing. Notice that all the matrices I used in Gaussian elimination, so the matrices I was multiplying with the original system to convert it to upper triangular form, that they were lower triangular. They were actually more than that, right? They were just diagonal ones, plus one off diagonal element, but it was in the lower triangle, right? So again, this picture. The lower triangle and upper triangle. So all the matrices I was multiplying with, they had ones here, ones on the diagonal, and there was only one of diagonal elements, some a, somewhere in this area, in the lower triangle. For example, let's recall them. One of them looked like this, right? It's interesting, it's relatively simple to find the inverse matrix. If I have a matrix like this, it turns out that all I need to do to invert this matrix, I flip the sign of this single off-diagonal element, right? Let's verify that this really is an inverse. So to the first row, nothing was happening, right? So that's fine. I'll get 1, 0, 0, obviously. So I'm doing this multiplications. So I'm just letting through the first row. The second one, I do 2 minus 2, so that's 0. That's good. That's what I wanted. Here I just get 1, and here is just 0. 2, 1. This is this dot product here. And the last one, it's again, it just copies the third row. So this is an identity matrix, I. And that shows that this indeed is an inverse to this matrix. And important thing, notice that the inverse is also lower triangular. That will be important. So one more thing that we can notice is that if I multiply two lower triangular matrices, I get a lower triangular matrix back. I think it's sort of obvious if you look at the graphical representation of the matrices. If you wanted, you could prove it formally, of course, but I don't think it's that interesting thing to do. Let me just try to draw it. It's supposed to be the same size. So they are both lower triangular. So if I'm taking guy like this and multiplying with something like this, so here is the area where everything has to be 0, right? So if I'm doing dot product of, like, for example, these two, this row and this column, so here is something non-zero, but it has to hit zeros here, right? And the same way here, there was something non-zero here, but it has to hit these zeros. So the result is just like a very intuitive graphical proof. If you want, you can do it more rigorously, but I don't think there is any point. The point is that the result will have also no zeros at the upper triangle, so it will be lower triangular matrix. So the product of two lower triangular matrices is still lower triangular matrix. The same there for upper triangular matrices. If I take two upper triangular matrices, I'll multiply them together, I get an upper triangular matrix back. And that is interesting, because if I put all these things together, I get our first matrix decomposition, the LU decomposition, which is essentially like a fancier name for Gaussian elimination, if you think about it. So here is yet once again, just now in terms of letters as opposed to actual matrices, written the process of Gaussian elimination, right? Sort of nice that you can like write it just abstractly, right? Because I start with some matrix A, and I'm applying these elementary row operation. That's the term I was blanking on. So these L matrices are the elementary row operations, or the individual steps of the Gaussian elimination. So those are our L matrices. I need to apply n of them to get to upper triangular matrix U. And so remember, here is the cool thing. Remember that inverting every single one of these is simple. All I need to do is flip the sign of the off-diagonal element, right? And with the matrix inverse, it means I can multiply both sides of this equation with the inverse of Ln, right? So I can I can get this. Ln inverse u, right? Then I can do the same thing with Ln minus 1, and again exchange it for its inverse over here. And eventually I get to this form. I get that A, that was my input matrix, that was the system matrix, can be written as a product of these inverses of the elementary row transformation matrices. I think that's how these L's are called, elementary row transformation. It doesn't really matter what they are called. What matters is how do they look like and what do they do, and that they can be inverted, and then the inversions I can multiply together. And because multiplication of lower triangular matrices is still a lower triangular matrix, so if I multiply all of these guys together, I get some matrix L, which is still going to be lower triangular matrix. And I can say that A is L times U, where L is lower triangular and U is upper triangle. And this is what is called LU decomposition. Essentially, it's just like a pure matrix counterpart to Gaussian elimination. The cool thing is that now I don't have to even think about any. Yeah?
So for the Gaussian elimination, can you use upper triangular matrices for all L's and then get a lower triangular matrix?
Not sure if I understand what you mean. Use upper triangular matrices for.
Like the L's.
So the L is like low, L is like low, and U is like up. So L are the lower triangular ones, and U are the upper triangular ones.
Can we use upper triangular matrices for L?
Oh, for, I guess you could, but that would correspond to column operations, and you have to multiply from the right.
That would also work.
Yeah, that would also work. It would really be the same thing. It would just be all transposed, except that we didn't talk about transposition yet. But I don't know how else to answer your question. But yeah. Actually, it's a good insight that you can always look at it too. I think you maybe already know about the concept of transposition, or that you can always look at it two ways, right? It's similar like looking at vectors as row vectors or column vectors. In both cases, it's essentially the same thing, except that we are looking at it slightly differently. So yeah, that it would work. It would do the same thing. So let's illustrate this LU decomposition on our favorite system. This is the example I started with. And here are the lower triangles that I used to convert it to upper triangle. And here is exactly what was written here previously in the general way. So I take this matrix, takes its inverse, put it here. This is the inverse of this matrix, and this would be the inverse of this matrix, right? So notice that the inverses only flip the sign of the off-diagonal element. And here comes the beautiful thing of matrices, that I can multiply all these guys together. And the even more beautiful thing of lower triangle matrices is that this stays lower triangle. So if I multiply these three together, I get this thing here. And this product is just the original matrix back. So this is our first example of matrix decomposition. Matrix decompositions are super useful thing. We will end the course with singular value decomposition, which is probably the most important matrix decomposition, which we will get there. But already this one is very, very, very valuable, the LU decomposition. Why it's valuable is because we can easily solve systems with it, right? Which sort of makes sense, but let's look at it how exactly it works. And then I will explain why it's actually a better idea to, like, if you are coding things up, it's better to like program the LU decomposition rather than solving systems repeatedly over and over again. So if I have a matrix and I have its LU decomposition, then solving systems of the form AX equals B is very simple. If someone gives me the LU decomposition of A, I can solve these systems for any B very easily. That's because I can, so if A equals LU, I can write it like this, right? LUX equals B. And here is a slight trick. So I first solve LY equals B. What is the Y? That's just some auxiliary variable. Some temporary thing I introduced there. Some temporary vector. And the second step, I take this U and put it on the right-hand side, and I solve for X. The X is going to be my solution. The X is the same as this X. That's my unknown. Obviously, you see that it works, right? Because if I plug this Y here, I am at LUX equals B, and this was A. So indeed, this is solving the original system. And why is this reformulation useful? Is if you are in a situation where you have a constant matrix A, but you have a lot of right-hand sides B. Somebody keeps giving you new and new right-hand sides. That happens actually quite a lot, for example, in physics. Like if I have like some elasticity problem, which is described by a matrix, it's like a linear elasticity problem described by a matrix, and like some elastic object, and somebody keeps giving me different B's. The different B's can be like constraints, right? So I have some like elastic sponge or something, and the B's could be telling me where some two handles of it should be stretched of that sponge, like that. So the B will be changing a lot. That's like something the user will be manipulating interactively, but the A is going to be constant. And that's where the LU decomposition would be super useful, because you only need to compute the LU once. And once the LU is computed, then for arbitrary new B, computing the solution is very fast, because both of these are essentially back substitutions. Or sometimes this is called like forward substitution, and the other one is called back substitution. But in both cases, it's really simple. Just sweep through the matrix, and you get it. What is the complexity of the? I'm just thinking, what is the time complexity for the forward or back substitution? If I have a matrix of, say, square matrix n by n, then I believe the complexity is quadratic, right? Because I just have to go once through the entire matrix. Yes, it's quadratic. So here is something illustrated with our favorite example. So if I took matrix A, so before I was solving it like directly from matrix A, but now I assume somebody gives us already the LU decomposition. By the way, if somebody gives you LU decomposition, it's trivial to verify if it's a correct one, right? If like you call the solver in MATLAB, maybe there's a bug in MATLAB, right? So you don't have to trust it, but it's super easy to verify, right? All you need to do is check that this is a lower triangle. That's embarrassingly simple. Check that this is an upper triangle. Just check that there are zeros, and then check that the multiplication works, right? And you verify that you got a correct LU decomposition. And once you have a correct LU decomposition, then solving a system, for example, this is very simple, because I first use the L and I use the temporary auxiliary variable y, and I solve it with the original right-hand side, and I get some value for the y. And then I use this y and plug it on the right-hand side of the U system. So I solve Ux equals my y. And the x I compute is the solution to the original problem, Ax equals right-hand side. Yeah? So what is the computational complexity of Gaussian elimination, or equivalently LU decomposition? So here is written that it's O(n) cubed. It's good to think why is that. Again, I always have to think about it again. So we are working on a matrix, right? And we are first we have to eliminate this entire thing, right? We have to get zeros here. And we get them here by scaling the first row and adding it to all the other rows, right? So if this is an n by n matrix to begin with, n by n, this will take O(n) squared operations, right? That's the first step. In the second step, I need to do the same thing again, except that I need to get the zeros here, right? So that's another O(n) squared operation. And I have n columns, so altogether, if I sum this together, it will be O(n) cubed. That is not great. That's fine for small matrices, like if n is like 3, it's a joke, right? If it's like 10, it's still a joke. If n is 1,000,000, that's not a joke. Or it's also a joke, but like it's a joke that somebody would ask you to solve it, because it's not going to happen, right? 10 to be like 10 to 11. So that would be pretty crazy problem. Now, fortunately, we often can exploit some special structures of the matrix. Very, very frequently, more often than not, it actually happens that the input matrix is sparse, that it has lots and lots of 0 elements. And there's like basically a whole industry of sparse linear solvers, because it's super important applications. All these problems from like fluids or elasticity or whatever else can you think about, they usually end up with a very sparse matrix. In sparse matrices you can solve or decompose in faster time than asymptotically better time than n cubed. So if the matrix has such a special structure, it's almost mandatory that you exploit it if you want your algorithm to perform reasonably. Now, for the simple things we will be covering here, I think this is the dense case, right? It doesn't mean that there could not be zeros. It just means that you are really performing the computations with all the zeros, right? That you are really like doing 0 times something. If there's like lots of zeros, the thing is, the point of the sparse routines is that you design your algorithms in a smart way, that they are actually skipping the zeros, that they are not doing stupidly all the calculations 0 times 5, 0 times 6, 0 times 17, and so on, because it knows that it will always be zeros. It's just arranged smartly. I'm saying this because, like, I've seen many times people using just the dense routines and then being surprised that it's like infinitely slow when n is larger. So that's what it's supposed to be. If you're using dense linear algebra, things like LU for large n will scale really poorly. It's n cubed. It's not very good scalability. So there is more issues with this, which has to do with numerical precision. I'll discuss about that in more details the next lecture, because there is like there's like a whole can of worms essentially, but it's not that bad. So I'll just remind you that whatever computations are we doing on a computer, like usually they are only with finite precision arithmetics. It doesn't mean that you could not do exact computations. Like in some software you can do exact computations, but that's going to be way, way, way slower. It cannot use the hardware. The hardware, like the floating point units, it's either single or double precision, either 32-bit float or 64-bit float, the double precision. And both of them, they introduce rounding errors. And we need to be very careful about these rounding errors when solving linear systems, because sometimes it can happen that these rounding errors, even though they are all very small, it can happen that these small errors have a huge effect on the result. So that's what I will explain in more details later on Wednesday. Any questions? All right, so thank you.